Okay, so I will talk about multi-phase problem, which is the main topic of tutorial in Wednesday, I think. So it's about dynamic data structures. We heard about them in the morning, so we just like store some data in the memory, make some updates, and we want maintain efficient updates and queries. So I will skip these. I think everybody knows here what's dynamic data structure. Okay, so like the long-standing open problem here is to prove unconditional lower bounds on trade-off between the update time and query time for adaptive data structure. It means that what cell we probe next depends also what we saw in the so far probed cells, and because for non-adaptive data structures, the proving of such lower bound is quite straightforward. So the adaptiveness is really like the big deal here. Okay, so one dynamic data structure problem was proposed by Patrashku, and so in this problem we had three phases. First is preprocessing. We got some k n-bit string x1 up to xk, and we want to preprocess it somehow into our memory. So we create some table. Each cell has W bits. We have S cells in our memory, and we want to compute this table, let's say on RAM machine in some preprocessing time TP. And so we consider k and s the parameters to be polynomial in n. And w is, let's say, logarithmic in n. That's like standard setting of these parameters. So the second phase is update. We get another y, another string of n bits, and we want to update our data structures, and we consider it as a decision tree. So we just read some cell C, and according to its value, we can update into the cell, and then read another cell according to value in C, and then we continue, and we want that the depth of the tree is our update time. So that's the second phase, and the third phase.
Just one thing. Can you assume without loss of generality that you're not actually overwriting any cell? Just like have some empty cells at the end to which you will write like any additional information? To not like
yes. You can. Yeah, actually, this this talk will be also a little about it.
Okay.
And yeah, you can do that. You don't override the cells, but actually write into the cells at the end of the, and somehow these two models in this setting is basically the same. And yeah, the last phase is the query, which is index to the first k strings you get in the first phase, and now you have just a query decision tree. You query the cells, and at the end you want to answer the question if like the strings xy and xi and y are disjoint when we consider the strings as a characteristic vectors of sets. And our query time is the depth of this query decision tree. And of course, we can generalize this problem that at the end we don't want to answer if the strings are disjoint, but some arbitrary function. Okay, so summary of this problem once more. We have preprocessed case strings, then we have one update, and then we have the query, and we want to answer if the string xi and y are disjoint or not. So we have two trivial solutions for this. One is somehow long update, and one more thing, like during all this talk, I just assume that the preprocessing time is polynomial. We are not very interested in the preprocessing time. We are interested in trade-off between update time and query time. So one trivial solution is a long update, and so it pre-compute all the results for all x1 up to xk if they are disjoint with y or not. And then basically our time for the update is k times n, because we need to read k times n bits. And the query is then is constant, right? We just we have array of the pre-computed solutions for all queries. So on the other hand, the other trivial solution is a long query, which says that we compute the disjointness of xi and y in the time of the query, and we need to basically read the bits of xi to answer that query. And yeah, it's somehow tempting that these are like optimal solution, and Patrașcu somehow propose some communication game that you can good. And you can reduce the data structure to that communication game, and if we would have the lower bound for the communication game, we would get the lower bound for the data structure. The communication game is the following. So it's a three-party communication game. We have Alice, Bob, and Charlie. And so Charlie got all the x's and the set y. Alice got all the x's and the query I, and Bob got the y and the index I. And it goes in follows. So first, Charlie send a private message to Bob, and it's basically the update of the data structure. And then after that he's silent, and Bob and Alice needs to compute if xi and y are disjoint or not. And the idea is that if the update is, let's say, little o of k times n, then Bob has so much, so small information about x's that.
And you mean little o of k? He can just send all of the answers, and that would be k.
Little of k. The n should not be
Oh, yeah, sure. Then, yeah, so Bob has so small information about the result that basically they have to compute the disjointness, which means that communication lower bound for disjointness is omega n. So it's tempting somehow that these are optimal, but not. Arkadev and Tony and two other guys has a result that actually you can solve this this communication game with update time and query time in square root of n, and you can translate this also to data structure. So this problem for disjointness has some non-trivial solution. And yeah, and Patrashku conjecture that there is some delta or some tau bigger than n2 delta, such that update time is n times 2 delta and query times is at least n times 2 delta and query time is at least tau, which means that basically you need at least n2 delta time to process one bit. So he conjectured that this is the hard problem for dynamic data structures. And a few years ago, Yang and Omri come with some lower bounds for that problem, but for some restricted data structures, which they called it semi-adaptive data structure. And so basically they prove the matching lower bound for the upper bound given by Arkadev et al. But for somehow weaker notion of data structure. And okay, so what's semi-adaptiveness? So update phase is completely adaptive, but the query phase is somehow there is some structure in adaptiveness. So consider the data structure after the update, and we have some original cell and some updated cells. And during the query phase, first the decision tree queries some of the original cells, and then the updated cells. But so after it started to query the updated cells, it does not have, it cannot probe the original cells no more. So this is the notion of semi-adaptiveness. And what we did with Bruno is that we generalize this theorem basically for any function, that we don't prove it only for disjointness, but for arbitrary function, and we replace the lower bound for the query time by the we replace the square root of n by corruption bound of the f of the function we are interested in. So what's the corruption bound? I assume a lot of you knows what is it, but to be on the same page. So let's have some function with two inputs, and we create a matrix such that so once rows are indexed by the set X, and columns are indexed by set Y, and if we have some particular input of the function, so the entry corresponds to X from X and Y from Y, so the entry is the result of the function on that particular input. So we have such matrix, and if you look at the rectangle of that matrix, then the function is Boolean, so we see the zeros and ones in the rectangle. And we also fix some distribution on the inputs. And we said that the rectangle R is the raw, almost the B monochromatic, if so rho is some small constant, and we want that if B is let's say 1, that the zero part is really small according to the size of the rectangle, and we measure the size of the rectangle by the distribution we are interested in. So this is a notion of almost monochromatic rectangles, and we said that the function has a corruption bound under the distribution mu at least S if there is B equals 1 or 0, such that any almost monochromatic rectangle, B monochromatic rectangle, has the size, again measured by the distribution, at most 2 to minus S. So what does it say? That under the distribution, any almost monochromatic rectangle is small. So this is somehow let's say classical notion from communication complexity lower bounds, because this measure lower bounds the randomized communication complexity of the function. And it's related with discrepancy, which is maybe also more known notion. And so discrepancy measure maximize the biasness of the rectangle. So it's if the discrepancy is small, it means that all big rectangles are unbiased. It means that zeros and ones in all big rectangles are almost even. And these two notions are related, because if the discrepancy is small, it means that for all B's, means 0 and 1, the size of almost B monochromatic rectangle is really small. And it implies that the corruption bound is bounded by logarithm of 1 over the discrepancy. So it means we have our lower bound in terms of corruption bound, but this translates that if the function has small discrepancy, it also applies for. Yes?
What about other measures in communication complexity? I mean, does your lower bound also hold for like information complexity or smooth rectangle bound?
I think a rectangle bound is basically the corruption bound, right?
The smooth rectangle.
Yeah, actually, our proof is for smooth corruption bound. So yeah.
When you write CB of F without the superscript and subscript, right? Then, well, on the previous thing, when you plugged it in, there was no super or subscript.
Sorry. What do you mean?
Well, you write just CD of F. So
Yeah. Here I just forgot to. Yeah, this is some informal statement. I will get back to it for the formal statement of the theorem. So.
Which will give the quantifiers.
Yeah.
Didn't we say that you can never get a query bound which is higher than the product communication complexity of the function, right? If a function f has a cheap protocol under product distribution, you cannot hope Arkadev and Tony showed that you cannot.
Our bound our bound is true only for product distribution.
Oh, it's corruption under product distribution.
Yes,
Oh,
yes.
okay,
Then
okay. I see.
and then like corruption bound under product distribution of disjointness is square root of n. So we.
Yeah, I was worried that the corruption can be higher.
So, our result, I hope, is not in contradiction with Arkadev. So. Okay, so this is a corruption bound. One thing, one other notion we need to form a statement. Our theorem is what's a balance distribution. So distribution is balanced for some function f if the probability of that the function is 0 and the function is 1 is at least alpha. So somehow both the zeros and ones in the overall matrix is somehow high. Okay, so now I will restate formally our result. So I was already talked about it. So what's a product distribution? So we have distribution on inputs, and the distribution is product if there are two independent distributions, mu1 for x and mu2 for y, such that the overall distribution is just product of these two. And so the formal statement of our theorem is that, so let's have some alpha and distribution over input, that is product and alpha balanced. Then it says that any semi-adaptive data structure for the multi-phase problem for which computes the function f must have either long update or the query time is this. So here is like the quantifying of the parameters for Mike. So we need to find a hard product distribution when the function has high corruption bound. And as I stated, we have a slightly more general proof. The same result also holds for randomized data structure, for partial functions, and instead of corruption bound, we can state it with smooth corruption bound, which is slightly general notion. So just for applications of our theorem, so we have a linear lower bound of query time for inner product, because inner product has a small discrepancy. We have a square root of n lower bound for disjointness. So the same result as Omri and Dianghe, and it's because it has a large corruption bound. We have a lower bound for gap Hamming distance, and it's done through some reduction from other functions. So, okay, so what's the proof ideas of this? So Yang and Omri use the following. So from they have some random variables for the multi-phase problem, and from the data structure they get some other random variable z, and there is some middle communication problem, but it's a like a weaker communication game, and they introduce like the fourth party in it. I will not talk about this one, but they have some properties. They prove some properties about z, and basically they derive some random variable that is similar to communication protocol. So the first property is that the last bit of z is the disjointness of x, y, and y. So the last bit of z is the answer for our problem. And then they said that the information between xi and z and y and z is at most the query time. So this somehow means that if z is communication protocol, this holds as well, and this would be the length of the protocol, and it says that somehow any protocol induce a partition of the matrix into rectangles, and somehow if we have protocols of length c, then we have at most 2 to c rectangles, and this says something like that from a like information theoretic view, that the information which has z about the inputs is not very large. And the last thing is that the information what between xi and y given z is very small, and for communication protocol this quantity is 0, because we are partitioning the matrix into rectangles. So this something said that our random variable z partition the matrix into small number of things which are almost rectangles. So this is somehow intuition, and in our paper we prove that basically this intuition is right. And so in paper of Omri and Young, the last thing they proved that such random variable z does not exist for disjointness. So in our paper we just replace this last step and says that if such z exists, then function f has for both b equals 0 and 1 large almost b monochromatic rectangle. So it means that f has small corruption bound if the data structure is somehow effective. So how to find such a such large almost b monochromatic rectangle? So once again, we have this protocol-like random variable z. And so first step, what we did is that we fix the random variable z into some specific value, such that the last bit of our fixing is b. We can do this fixing for both b equals 1 and 0 because f is balanced. And then according to our fixing, so the information between xi and y is still small. and Kyle divergence, which is also some information theoretic measure between the xi and xy condition of that we fix the z, and the same with y is still small. And these two things are basically because like these two information are expected values of these two measures. So we.
I think the order is the other one between the xi and the condition xi.
Yeah, that's maybe right. Yeah, because a Kyle divergence is not like symmetric, so yeah. Okay, so we just fix our z, and then so we have this distribution of xi and y given conditioned on this fixed z, and we look at the support of this distribution, and we know that the result of the function of the support is b. Then we look at the mu prime z, which is the product of the marginals. So we look of the marginal distribution of xi and y under this distribution, and look because the information of xi and y given this z is small, it says that these two distributions are very, very similar. But the support of mu prime z is now rectangular. But because these two mu z and mu prime z is very similar, it means that the new added elements has a very small probability. So therefore, if we look of the support mu prime z as r prime, then it's a rectangle and almost be monochromatic. And then we make buckets on the xi side and y side, and we define the buckets that the elements which are contained in one bucket. It means that the probability of those elements under the marginal distribution mu zy is some roughly constant factor of the original distribution of y, and same with xi.
Sorry, could you say that? So how are these buckets defined again?
Yeah. So we put into one bucket such elements that okay, so maybe more formal. It would. So we have so we have elements of the set y, and we have two distribution over y. So mu2 is our original distribution with for which we want to prove like the large corruption bound, and mu prime zy is this marginal distribution from this one. And now we for each we compute somehow this fraction for each element, and we group into one bucket the fraction which are somehow very similar. Is it clear now?
I think so.
Yeah. So basically, like all elements, for example, in this bucket, all elements have like the probability under this distribution is c times more than under this distribution. And,
So it's just, I mean, so that you want each little box to be roughly uniform, is that the?
No, like roughly not uniform, but all the probability under this distribution of all elements in this bucket is a multiple of the same number of the probability under the original distribution.
Oh,
If you draw the scaled version of mu, you have the original mu, and then you look at all the elements where the ratio is rough.
Yeah, and because the Kyle divergence is bounded, we can prove that the number of these buckets are small, and also the value of these constants are not so big. And therefore, because there are small number of buckets, then we know that there is almost monochromatic rectangle which is larger under this mu prime z. And basically, the probability of R under the original distribution is C1 times C times smaller than under mu prime z. So, and C1 and C2 are small numbers. Therefore, it's also large under the original distribution, and that's how we find our large monochromatic rectangle. So that's all for the proof. So I would like to conclude with some open problems. So these are already stated in the original paper from Omri and Yang. So how powerful are semi-adaptive data structures? So are they like as powerful as the full adaptive data structures? Is there some separating problem? So that's one question. Sub-question is that this is proof when first we query the original cells and then the updated cells. So can we prove for more alternation? So first we query the original cells, then the updated, then the original, then the updated. Can we generalize the lower bounds for that? Somehow meta question is somehow could this combinatorial understanding of this information theoretic properties of the variable z could it help to resolve these questions? Also, could we generalize the main result even for non-product distribution? And yeah, that's all.
Regarding one, I think Omri's paper has like that any such technique would not be able to use the multi-phase game, right? Like if you allow even two messages of Al or Al.
Yeah, we discussed it with Yang in today lunch. That we need other techniques for that.
So at the beginning you mentioned that for non-adaptive data structures the proof is usually?
Yeah, it's
So is it like, I understand that
it's
adaptive would imply it, but are you saying that there is an easier proof?
yeah, there is some proof using like incompressibility argument, something like that. I read the paper many years ago. So, but like my impression from that is that there is no such big deal to.
Which paper? The original?
It's I think.
Maybe Casper could say something there.
Yeah, I think it's called adapt or die or something like that.
I see. And where, I'm sorry, I maybe missed it, but where did you use that
So the Z only holds this only good properties only when the protocol is similar. If the alternation goes over even 2 or 3 between Alice and Bob, the Z doesn't have those nice properties.
I see.
Yeah, exactly. To the existence of such Z that.
And what about like not alterations, but like start with the updates and then switch to the non-updates?
Even that fails for us, I think. I don't know.
Yeah. So far, I have no idea how to improve it.
That sounds a little unusual at first.
Yeah,
But technically we cannot.
I see.
Our proof cannot handle this.
So Pavel, in your the open problem section. Yeah. So point 2. What do you mean?
Sorry.
The last point. Yeah. What do you mean exactly by that?
Well, we prove it like our theorem holds only for product distribution. That if you.
But there's no hope of proving it for non-product distribution.
But the upper bound, it only kills you if it's non-product distribution. Right? So that's what I.
No, because there's a better upper bound for. I mean.
Yeah. So.
These two things can be arbitrarily separated. So for set disjointness is already quadratically separated, but then there are functions for which the product distribution would give you constant lower bound, and the non-product distribution would give you linear lower bound.
I see. Okay, so maybe for other notion than corruption bound or something like that, because so far I don't know a lot of interesting stuff is done for product distribution, right? So non-product distribution is somehow hard.
More
questions?
Well, I have a question, but only if it's, I don't know how long the answer will be.
Okay.
How hard is it to tell us what the random variable Z is?
Well, I don't remember it.
I mean, it's just
it's
some description of what the data structure is doing.
Yeah. Basically, Z contains some of xi's and some of the transcript for some of the indices. Am I right? Something like that.
Even I.
Oh, okay. Then I don't have to answer this question. Yeah, it's it's some standard thing that there isn't no something very strange.
One of these direct sum arguments
Yeah,
that you sample.
kind of direct sum, but you need some further properties of the embedded coordinate. So it's like a projection to a single coordinate, but it has some more bells and whistles that I don't remember actually.
And is the protocol, your protocol, is it semi-adaptive?
Yeah. I think in your protocol you don't query the original cells at all, right? I have such feeling that maybe I.
It's like a 1.5 round protocol, right? Like C speaks to B, B speaks to A speaks to B, and that's it. If I recall correctly.
But is the protocol for equality also semi-adaptive in your paper?
Yeah, it's even simpler.
Oh, I see. All right, let's think.